and thank you very much for this nice opportunity to be here in Tampa, in Florida, to speak about the interesting things. The things that I think are interesting is triggered incommensuration in Burkovsky crystal. This is a study which has been performed by a collaboration, which is in part in Russia at St. Petersburg Polytechnical University, in part at PbHfO3, in part at synchrotron at Grenoble, and in part in Poland, two Polish universities. What I would like to tell you, there are three experiments which show three different things. One thing is that we found cubic to incommensurate phase transition in Burkovsky. Second is that the transition doesn't have the incommensurate soft mode. There is no incommensurate instability. Third, there is a strong anti-ferrodistortive instability. And by analyzing everything within Landau theory, we show that it is this anti-ferrodistortive instability which creates incommensuration in perovskite crystal. What is incommensurate? People often ask what it is. A good example is our solar system. Let's say there is a period, number of seconds in the year, number of seconds in the day. If you try to calculate, you never converge to the rational number. So the number is irrational. So that means that the day could be a little bit longer or a little bit shorter, while keeping the year the same duration. So this gives a freedom. So one rotation is decoupled from the other. How it occurs in the materials? In the materials, we often have the periodic potential and additional interactions between atoms. For example, between displacements of the ions. And if the system respects very much the potential is very influential, it becomes commensurate because it's energetically favorable. But if the springs are more important for this system, it doesn't care about the potential and lives its own life, and it is incommensurate. So you change a little bit temperature, a little bit pressure, and these springs are normalized, and the period of the modulation changes. This is what is incommensuration. How it typically occurs in dielectric materials. There is a big book by Blitz and Devanuk, which explains different crystals from which potassium selenide is the most important, the most well studied, and how it happens there. There is a soft mode which does soften on temperature degrees, approaches zero, and when it does happen, you obtain the modulation in the crystal. So the softening of the phonon, the freezing of the phonon results in the formation of long-range incommensurate order. Then this modulation evolves with temperature, and finally it becomes commensurate in the Logan transition. What would be the good example from the family of perovskites? Good example is lead hafnium. It is similar to lead zirconate, which is heavily studied, a lot of talks about it. What makes it different from lead zirconate is this intermediate phase. So this is a cubic phase, this is anti-ferroelectric phase, which is isostructural with one of PCO. And this is intermediate phase, and people try year after year to solve the structure with, let's say, increasing success. And recently, in 2018, there was a paper of Hideshi Fujishita, I think the third iteration. So they finally have shown that the structure is like this. I don't know what about you, I don't understand what is there. But for simplicity, I have drawn how it should be perceived. So this is a structure with a log period modulation with transverse waves. It is very similar to the antiferroelectricity, but the modulation period is larger. But with Yoshida, he doesn't say that it is incommensurate, he just says that it is non-period. So we are curious, we try figuring out whether it is incommensurate. Important thing, it is that not only shifts of the patterns are here, but also there are antiferrodistorted tilts, 2 order parameters. This is our experiment. We put very, very strong synchrotron light on this crystal to have many, many, many orders of the reflections of big orders from 7 to -7. So this is the parent reflection, first, second, third, and finally, when you jump over the brilliant zone, you arrive here, this is the 7. So the whole brilliant zone is jumped over by this incommensuration. What is good is that you can be very sensitive to the changes in the modulation wave vector. This is what's happening with temperature on this structure. It starts from particular place when these 2 reflections overlap, and then they evolve with temperature quite smoothly. A large picture is, you see this intersection of the second order and -5 order. It allows to reconstruct very precisely the modulation wave vector. Typically, in incommensurate systems, you should have, it is not here for some reason, but you have staircases, like devil's staircase. You see nothing like that is here, everything is very, very continuous. So this is just incommensurate phase. How it forms this incommensurate phase? This is a puzzle. Diffuse scattering, it reflects the susceptibility with respect to modulations. So if there would be a soft mode, we should see it here. But we don't actually see soft mode here. We see diffuse scattering centered at the zone center and no specific peaks at incommensurate positions. So for comparison, this is what occurs under pressure in lead zirconate, where there is a clear incommensurate soft mode. And this is lead zirconate ambient pressure, which is pretty much the same as this lead half. We try to dig, maybe there is some incommensurate soft mode, we don't see it. We tried fitting. We made several profiles at many temperatures and fitted them together. And using the standard expansion of Landau potential, which is used for ferroelectrics, for normal ferroelectrics. And it seems that this lead half magnet obeys very nicely this ferroelectric susceptibility function. So it is just a ferroelectric in the cubic phase. No traces of incommensuration. This is what to compare to. This is lead zirconate under pressure. You see very, very nicely that incommensurate soft mode condenses. Here you don't see anything like that. So no incommensurate soft mode. What kind of soft mode could be there? Of course, we look at the antiferrodistortive instability, which is common to perovskites, and look by inelastic X-ray scattering and see what's happening, true photon resonances, and constantly growing central peak. But to think about growing central peak, we have already the receipt from the past. It is strontium titanate. When you approach the antiferrodistortive phase transition in strontium titanate, you see a peak which is very narrow in energy and which is growing very much towards the transition. So the soft mode, it goes into that peak instead of the photons. This is a complicated formalism, but generally soft mode is central peak. We think that it is the case here. So whether, so how could we estimate the frequency of the soft mode? To understand that, we separated the two contributions to this spectrum. X-ray people would appreciate that very much because typically it is not very easy. So we understood that these photons are from lead motion, and the central peak corresponds to the antiferrodistortive tilts. So the intensity of the central peak is basically an estimate of antiferrodistortive And we see that this susceptibility grows very, very sharply on approaching the transition temperature. At the same time, you can compare that to other susceptibilities that exist in the system. Which susceptibilities are there? Incommensurate softening, a little bit soft position at the incommensurate wave vector, and we see that it is almost temperature independent in the relevant temperature range. There is a ferroelectric soft mode, which softens much better than incommensurate order parameters. So ferroelectric soft mode is normal ferroelectric soft mode, which was known as crystal. And AFD softening is the largest. So we should think that maybe it is even the most important. We should appreciate that a little bit afterwards. After considering the Landau expansion, how it should look like. The symmetry level form is this one. These are the modulation magnitudes, and these are anti-ferrodistortive tilts. So these three charts describe first order phase transition with respect to the modulations. This describes anti-ferrodistortive tilts, first order phase transition. And this is the biquadratic coupling allowed by symmetry, which has to be attractive in order to have simultaneous appearance of the order parameters. This is very similar to the example which is well known. It is Holakovsky trigger mechanism for ferroelectricity. So Holakovsky considers that there is a crystal with no ferroelectric soft mode. So there is no peak and epsilon. So nothing predicts any ferroelectricity. But there is an antiferrodistortive mode, which in principle could lead to the antiferrodistortive phase transition. But this doesn't happen because of the strong attractive biquadratic coupling between these two order parameters. So instead of getting the AFD phase, we get simultaneous appearance of both AFD and ferroelectric distortions at the same temperature. This is governed by this minimum in the potential, which is more deep than potential minimum here. So when the AFD mode softens, some minimum should appear here, but this minimum is more decisive. This is Holakovsky trigger mechanism. To take this Holakovsky mechanism to incommensuration, we have to be more complex. We have three parameters: wave vector, modulation amplitudes, and antiferrodistortive parameter. And all of them should be non-zero. This is seemingly quite complicated situation, but in fact it is not that complex. And we need biquadratic coupling, which is not arbitrary, but of some particular sort. It should be attractive, because otherwise we will not get order parameters together at the same temperature. It should have negative wave vector dispersion to compensate for the positive dispersion of the ferroelectric soft mode. How much negative should this dispersion be? We can estimate from the experiment. We did that, I just don't show because it's a little bit too detailed. And it should have a positive curvature. So if these criteria are met, so we have effective minimum in the stiffness landscape for the incommensurate order parameter. And it occurs simultaneously with the antiferrodistortive tilts. And in fact, two papers from the past do support this form of delta coupling. Delash and Miguez, they have shown that tilts should cooperate with antipolar displacements, which are in the incommensurate phase. But on the other hand, they should be repulsive with the ferroelectric polarization. So this gives a negative dispersion of the delta. So the summary. Experimentally, we have found a cubic to incommensurate phase transition, which has not been reported previously. So there were reports about incommensurate transitions under pressure from some non-cubic phase, which we now, today it is antiferrodistortive phase. So first evidence of cubic to incommensurate phase transition in perovskite. There are two ordered parameters. There is no incommensurate soft mode, but there is a strong anti-ferro distorted instability, which results in a strong anti-ferro distorted soft mode. And this soft mode makes simultaneous appearance of incommensuration and anti-ferro distortive order parameters. And this is very much Holakovsky-like trigger mechanism. So the receipt to have incommensurate phase in lead hafnium, and perhaps in many other perovskites, maybe all of them, I hope not. It is anti-ferro distortive soft mode plus collaborative coupling to incommensurate modulations. So it is very unexpected thing that incommensuration is not created by itself as it is used to be in dielectrics, but in perovskites it is different. It is created by the AF details. Thank you very much for your attention.
Thank you very much. The talk is open for questions.
There's another scenario, and the other scenario is from a paper we wrote with Holakovsky Triggered 2 years ago in PRB. And what we found is that there is a bilinear coupling between tilting and theoretic beta. So it's not Burkovsky-like, and it is driven by AFD. And what happens, because of this bilinear coupling, then basically you have incommensurate that can happen. We can also have a strange ground state of P0. So how do you distinguish, how do you know experimentally, how can you distinguish between what you propose and what we found by symmetry arguments?
I think I maybe not understand. You speak about bilinear or trilinear coupling?
Bilinear coupling.
Bilinear. Yes. So it's either
bilinear coupling.
Well, it's a complicated story. I mean, essentially, what you have in lead circonate, for lead circonate we did explicitly, is that the band that connects the ferroelectric soft mode merges with the band that comes out from the antiferrodistortive instability. So it's the same band.
this is bilinear coupling.
It's very flat, and essentially the minimum of this band could be anywhere. In fact, the phase of lead circonate could be understood as a lock-in phase for incommensurate phases that essentially are more or less the same. And what we showed in that paper is which parameters control whether you have a minimum at a rational Q or at 1/4, 1/4, 1/4. And so it's strongly related with the AFDs. There is also a trilinear coupling involved. So there is some sort of triggering, but we'll send you a PDF of the paper.
I would say I have some good answer to your question, to your good question.
I didn't ask any question.
Okay. So what you say is, let's say, why this bell is so broad. So this bilinear coupling explains why this bell is so broad, why it is not narrow. And it is different from biquadratic coupling.
Okay, well, indeed. I mean, so what Loan was trying to say is that we believe there is an alternative explanation without the need of a cooperative biquadratic coupling.
I think, perhaps you may be correct, but let's say presently I don't yet think so.
Sure.
Because let's say, if you have this bilinear coupling, you